Hi everybody, welcome to another video in linear algebra, section 1.4, the metric equations. What we learned in the previous section is that the system equation we can write as a vector form. In the vector form, we can say the last column is the linear combination of the column vectors if there is a solution. In this section, we explore the matrix equation. Right, so matrix equation A times X is equal to B. Right, if A is an M by N matrix, by M by N, meaning that have M rows and N columns. With columns A1, A2, AN. So we stack the vectors into a matrix. Of course, we did that in the last section. We stack all the vectors into the matrix like this. It's the matrix A. Right. Then the product of the vector, the matrix A with the vector X, denote AX is the linear combination of the columns of A using corresponding entry in X as weight. Right. So let A1 to AN be the vectors, and we stack them into the matrix. And the vector X has many components, but X is a vector, so it will be N component. So the matrix times the vector is given by this. It is defined if the number of columns of A equal to the number of entry of X. Right. Let's look at that. Look at this example. We'll see. So of course, if you take in this class, most likely you know how to multiply matrices, right? So when we multiply matrix, the middle dimension must match. So let's say we multiply this matrix with that matrix, which is a column matrix or vector. So this one has 2 rows and 3 columns, and this one has 3 rows and 1 column. When we multiply matrices, the middle numbers must match. And that's what we say the number of columns in A3 must match with the number of entry in X, also 3. If they do not match, we cannot multiply. Right, so how do we multiply this? By the way, when we multiply, the result is going to be outside numbers 2 by 1. So we're going to have a 2 by 1 matrix. Right, now the way we multiply matrices is by row by column. So the first matrix has these 2 rows and the second matrix have only 1 column. So we multiply row by column. The first one we have 1, and then second one we have 4. So the first with the first, second with the second, and third with the first. So we have 1 times 4. So that is the first with the first, the second with the second, plus the last one with the last one. Of course, then we just add them. And then I'll do the same thing for second row. 0 times 4. I'm just going to use the default color here. -5 times 3 and 3 times 7. Right, so we have 4, 6 minus 7. 4 times 4 plus 6 is 10 minus 7, 3. 0, -15, 21. Of course, we can just use the calculator, but it is essential that we know how to do this by hand. 3 rows, 1 column, 4, 3, 7. I said we cannot hit enter here. If that happens, don't worry, just copy and paste and redo it. Yeah, so when we enter the entry, just use these arrows, don't hit enter until we're done. Right, so simple enough. Again, row times column, first with the first, second with second, third with the third, and then we add them. And as we see, the result is 2 row 1 column, so the outside number will give us the dimension of the product of the two matrix. This one is a 3 rows 2 column, and this one is a 2 row 1 column. Once again, the middle number must match, in which case the product will be just this. First with the first, second with the second, first with first, second, first, second. Right, A minus 21 minus 13, 32 plus 0, minus 20 plus 14, and let's check. 3 rows 2 columns, simple enough. Now, for vector v1, v2, v3 in R3, write the linear combination as a matrix times a vector. Right, so how do we do that? So first, we have a linear combination. Right, so think about this, it's just a 1 by 1 matrix. What we do is, can we write like this? V1, V2, and V3 times and so why, how did that work? Of course we use that, but the reason it works is, now think about this, it's just, consider that it's just a 1 by 1 entry, right? Even though it's not, but we write that as 1 by 1 entry. This is 1 row 3 column, even though it is the matrix, but writing in the vector form, we can think of this as a 1 by 3. This of course is certainly 3 by 1. Right, so the middle numbers do match. The outside give us the dimension of the product. And when we multiply, 3 times v1 minus 5 times v2 plus 7 times v3. So in that case, we when we have a linear combination, all of the vectors will be stacked into a matrix. So this is a matrix, and all the coefficients will be stacked as a column vector. So in that case, we can transform from a vector form into the matrix form, like that. Right. Now, write a system of linear equation as a vector equation involving the linear combination of vectors, and then write the result as a matrix equation, Ax times b. So now this is a good exercise just to see different forms of the same thing. Right. So I just write the left hand side. Let's rewrite the equation. There's missing x1 here, so I will write x1 plus just 1x1 2x2 minus x3 equal to 4 minus 5. Just put them in column. 0 x1 minus 5x2 plus 3x3 equal to 1. Right? So remember, from this we can write as the geometric matrix, right? 1 0 2 negative 5 negative 1 and 3. So we write that in this form, and we write that as a geometric matrix. With that geometric matrix, we have, if this has a solution, then we say for 1, vector for 1 is the linear combination of these 3 vectors. So we do have the vectors 1 0, and the linear combination, we have the variable x1 x2 x3 instead of c1 c2 c3. So we can write this in the vector form. And x3 equal to 1 0 2 negative 5 negative 1 and 3 equal to vector form 1. Usually a linear combination we can use any letters, but in the equation has x1 x2 x3, so we just use those 3. Right, and then from here we can put in the matrix form, where all the vectors will move into a matrix. And all the variables move into a vector. And the right hand side was still just that. So same equation can be written in geometric matrix, can be given in the vector form, and now in the matrix form. Right. Just want to do this real quick. If we want to combine the vectors, that will be easy, right? x1 times multiply x1 in x1 0, and then multiply the x2 in, and then the x3, and add the vectors x1 plus 2x2 minus x3. Of course, we turn the vector form back into a system of equation. So we just match the components. So I should be able to get comfortable with this notation. We can have in system equation or metric form, vector form, or matrix form. Of course, you see this and that almost the same thing, except we have the bar there. So the matrix is the matrix of the coefficients, or the matrix composed by the vectors of the coefficients. The vector is the vector of the linear of the weights, or the constant, the coefficient, if you will, the vector of the coefficient, and the last one, of course, just a vector. Right, so that is in the vector form and matrix form. Right, now if n by n matrix with column a1, a2, up to an, and if b is in Rm, then the matrix equation has the same solution as this. Of course, that's what we said. We can write the matrix equation into the vector form, which in turn had the same solution as the linear combination whose symmetric matrix is this. So we can go from the metric matrix, vector form, matrix form, and the linear equation. We can link all of that together. Right. Next, let matrix A is that, and the vector matrix B is that. Is the equation A times AX times B is consistent for all possible B1, B2, B3. So, of course, the equation, if we write it down, AX times B AX times B AX equal to B, that's what I mean. Right, X, 3 component, because we know this is 3 by 3, this is 3 by 3, the vector has to be 3 by 1, so the middle numbers do match. Now, is this consistent? Of course, so that in the matrix form. How do we turn this into the vector form? Of course, we just have the columns. Just say x1 times the column, x2 times second column, and x3 times the third column. So the variables or the coefficient will be multiplied to the vectors, and we put those coefficients into the vector and the matrix, and that. We in turn, of course, multiply down and combine, we have the system of equation. But bottom line is we just put that in the metric matrix. So the metric matrix just realized that we need a lot more space for this problem. Right. So 1, 3, 4, and B1, negative 4, 2, and negative 6, B2, and negative 3, negative 2, negative 7, B3. Sorry, I should have read the question before. Right, so we turn matrix equation into vector form into a matrix matrix. Now, is this one is the equation has solution, so we just have to do reduce row echelon form, and once again we do not have the numbers here, so that means we have to do it by hand. That's why we take a lot more space. Right, I try to write very small here. Hopefully it will fit in that space. Right, so we have the pivot, which is good. Now turn this to 0, turn this to 0. See if I can zoom in. Just put another box here. Right. Yeah, closer to the camera. So turn that to 0, that to 0. And the pivot is this. So I will keep the pivot based on row 1. If we want to eliminate an element in row 2, that means we have to add and replace to row 2. If we want to eliminate element in row 3, we'll add and replace into row 3. And we use opposite numbers to the number we're trying to eliminate. Opposite to that is 4, opposite to this is 3. Right, now we do those operations. Those two operations at the same time. Right. Try to write small, but I should from the get-go. Alright, first row will stay the same. 1, 3, 4, and B1. Right. Now, 4 times row 1, 4 times 1 is 4, minus 4, 0. 4 times 3, 12, and 2. 4 times 3 is 12 and 2, so that's 14. 4 times 4, 16, minus 6, 16 minus 6. 4 times B1 plus B2, well, that's just 4B1 plus B2. Alright, next, 3 times row 1 plus row 3, that is 0. 3 times 3, 9 minus 2, 7. 3 times 4 is 12, minus 7 is 5. 3 times B1 plus B3. Right, so let's check. Pivot here is 1, 0, 0. So good. Now we go to the second row. Now, if this divide by 14 to get back to 1, that's what we should do. However, if we do that, it looks like a lot of fraction and we don't have a lot of space. So let's just give 14 here. What we do here is the forward step, or turn this into the REF. So we don't do RREF, we just do the REF. Which means we're going to keep 14 as a pivot, but we just need to eliminate 7. So in that case, what we need to do, I'm just going to turn this into a 0. Eliminate. So I multiply the top equation by 1/2 and then add to the second equation. Multiply this by 1/2, that gives us a 7. in fact better, let's use negative 1/2. Now we use the 14 row 2, add to row 3 and replace to row 3. And then you say, why don't we turn this to 1 first? Of course we can, but if that is the case, then this will have to have a fraction here. Besides, if you notice 14 and 10, 14 is 2 times 7, 10 is 2 times 5. So this 2 and 3 will eliminate. So what we're trying to do is trying to turn this into the row echelon form. So we see what are the pivots, where the pivots are for that augmented matrix. In that case, we don't have to work too much with the fraction. Don't have to worry too much about the fraction. Right, again, write small. The first column and the second column will stay the same. Only the third one will change. Now, negative 1/2 times 1. Once again, make sure we multiply to row 2. So just negative 1/2 times 0 plus 0 is 0. Negative 1/2 times 14. Negative 7 plus 7 is 0. Negative 1/2 times 10. Negative 5 plus 5 is 0. Negative 1/2 times that. Well, and then plus 3b1 plus b3. Yeah, so that is the last entry. Now, and just like what we have on the previous problem, what we have here, we have the pivot. This, of course, if we divide by 14, turn into 1, which is the pivot, of course. Now this, suppose it is a pivot of the geometric matrix, and on previous section we know that the system has solution. We cannot have the pivot on the last column. If the pivot on the last column, if there's something other than 1 or something other than 0, it is no solution. Right? It's as simple as this. If we have 0, 0, 0, and we have something else, let's say 5, there's no way we have 0x1, 0x2, and 0x3 equal to 5. We cannot do that. So once again, we cannot have pivot at the last column. So I just say cannot have pivot at the last column. Otherwise, I mean, we cannot have this. If we want a solution, then we cannot have the pivot at the last column, because the system is consistent, meaning there is a solution. If there is a solution, this cannot be a pivot, therefore it has to be 0. So we just have negative 1/2 times 4b1 plus b2 plus 3b1 plus b3 cannot be 0. Alright, let's simplify. Negative 1/2 times 4 is negative 2, right? Plus 3. Negative 2 plus 3 is b1. And negative 1/2 b2. And then b3. Oh. So we cannot have this. Right. So we cannot have the pivot on the last column. So that means it has to be 0. Sorry. Right. Right. We cannot have the pivot at the last column because the system is consistent. It has the solution. So no pivot on the last column. So this has to be 0. So that has to be 0, meaning b1 minus 1/2 b2 plus b3 has to be equal to 0. So if we have 0 here, then we have infinitely many solutions. Of course, if we have 0, 0, 0 equal to 0, then we have infinitely many solutions. And this will be good if this is 0. So we try to make this into 0 so it has a solution. Would turn out to be infinitely many solutions, but we need that to be 0. So no pivot at the last column if we want to have solution. And no pivot means it has to be 0. Right. Next, a system of solutions. The equation ax equal to b has a solution if and only if b is a linear combination of the columns of A. So this will be a linear combination of those vectors. That's simple enough. Now, if A is an n by n matrix, then the following are equivalent. For each B in Rm, for each, meaning for actually for every B in Rm, the equation has a solution. If it is a solution, if it has a solution, then we can say the vector B is the linear combination of the columns of A. And because of that, the column of A have to span the space Rm. And finally, it has to have a pivot on every row. Now that sounds a little odd. But and then you say, on this one we do not have the pivot on the last one, right? Right? Yeah. But what this term is essentially is, let me just write, we have the vector A, I just want to say A1, A2, all the way to AN. So then the variable will be x1 all the way to xn. The n vectors, n components. And when we multiply together, what do we get? From b1 to what? It's not bn, it's going to be bm. Right. Think about this. This one, it has n columns, all right? But its A1 is in Rm. So m component. So A1 is a vector that have m components. And when we multiply this by n1, the middle number match, and this end up being an m by 1 vectors. So what we see here is A and B, the columns of A and B must be of the same dimension. Here we have 3 by 3, might not be obvious, but should we have anything else? Here, you see, the columns will be the same dimension as the last one, because the last one is the linear combination of those two, of those 3 vectors. So the columns of A and the last column B must have the same dimension. The variable may not be. Now, on the basis of why that we cannot have, why we have to have pivot at every row. Now, remember, this work for every B in Rm. So B1 to Bm can be any real numbers. Could be 0, but it could be something else. Now, get back to this. this have to work for every b. Think about that. So in that case, we have to have a solution so that we have the pivot on every row, and the pivot cannot be the last one, cannot be on B. Why? Think about this. If we put in the augmented matrix instead, if we have the pivot on B, essentially there would be some certain form like that. But that's very specific B in Rm, right? Since this work for every B, this have to work for every combination, and we will not have the pivot here because the pivot only work for particular case here. Since this work for every B, we might not have the pivot on the last we might not have 0 on the last one here. So in that case, the pivot have to be from A1 to AN. Yes, because the pivot on the last column only work for some particular combination. But we know that this theorem works for every vector B other than those values. So in that case, if we want the pivot have to be in this case. The pivot on the last one is very restrictive in some certain special case of B. But this one is not special. It works for every B. So that's for sure it's going to be, pivot must be in the matrix A. Now, think about this. When we do the reduced row echelon form, let's say for that one, it doesn't matter what we have on the last one, right? The linear combination, the reduced row echelon form will turn into this regardless of what we have on the last column. So if we have the pivot here, then it's guaranteed to have a solution, a unique solution. Yeah. So actually we will do that in the next section, where it says that when we do, it's only the columns that matters. The last one really determine the type of solution only based on the first one. The first the vector, the column from the matrix only. All right, now compute 8 with x. Well, that's easy, right? We've done that many times. 8 times x, matrix A, 2, 3, 4, -1, 5, -3, 6, -2, and 8. That is the vector. Now this is, that is the matrix, and this is the vector. And multiply just row times column. Row times column. The first row times this column, 2x1, 3x2, 4x3, -1x1, 5x2, minus 3x2, 3. 6x1 minus 2x2 plus ax3. Right. Of course, if we want to write in the vector form, as was with the question did not ask, we can just write this as x1 times 2, -1, and 6, and x2, we write that as the linear combination of the columns. Yeah. So the columns are the vectors put in the matrix, and the vector will be the coefficient of the linear combinations, or the weight of the linear combination. Right. Now, properties of matrix vector product AX. If A is m by n matrix and un V in Rn, C is a real number, then we have these properties. Right. We'll study this a little more later, but we say the square matrix with 1 on the diagonal and 0 everywhere else is called the identity matrix and denoted by I. It's not very clear. We will say I2 identity matrix 2 by 2 is going to be that matrix, and I3 equal to that. We have 1 on the diagonal, 0 everywhere else. We'll revisit that maybe even in the next chapter. Right. Next, let A be this matrix, and let P be this matrix, and B be that. Show that P is the solution of AX equal to B. So it's easy. We're just going to substitute P into this, and that's supposed equal to B. If that is the case, then we say that system has the solution, and B is a linear combination of these vectors. Once again, the columns in the vectors must be in the same dimension as the vector B on the last one. On the last one, we're going to stack that into the geometric matrix anyway. Right. So now we show that P is the solution. If P is the solution, that means when we substitute in, that equal to B. So all we need to do is just verify is A times vector P equal to vector B. And then we just write it down. Matrix A 1, 5, negative 2, 0, negative 3, 1, 9, negative 5, 4, negative 8, negative 1, and 7. That is matrix A. Now times the matrix B, 3, negative 2, 0, and negative 4. Now we just multiply. I'll use the calculator. Three rows, 4 columns. Right. 1, 5, negative 2, 0, negative 3, 1, 9, and negative 5, 4, negative 8, negative 1, and 7 times 4 by 1. I'm sorry, 4 rows, 1 column. Yeah, 4 by 1. 3, negative 2, 0, and negative 4. Right. Negative 7, 9, 0. And that, of course, is B. So yes, let's check. That check. So that means the equation works, meaning P is a solution of the system. So vector P is a solution of AX equal to B. Right, and use that to write a specific linear combination of the column of A. So if this is the solution, that means this vector is the linear combination of these columns vectors. Because it is a solution, so we say negative 7, 9, and 0 is the linear combination, and we want to write specific linear combination of the columns. And guess what will be the coefficient for that linear combination? Of course, that will be from the vector here. We have 3 times the first column plus -2 times the second column plus 0. Of course, 0 times anything is still 0. We just leave it at that. Times third column. But just write down. And then -4. So you see, so that's why we require to have the dimension of each column have to be the same as the last column vector. In that case, if it is the solution, there will be it will be a linear combination. The last column will be a linear combination of the columns in the vector in the matrix A. Right, that's what we have. So pretty much what we learned in this section is just a different form of system of equation, but we put in the matrix form. So we put in this form equal to b, as opposed to the vector form or the matrix form. Ultimately, we need to interchange between different forms of the same thing. So that's why we have this exercise. Complete the following table for the equivalence of different forms. So if we have that system of equation, how do we put in the matrix? The matrix will be the coefficient on the left and the constant on the right. Right? We have 1x, no y, -3 for z, 0x, 2y, 1z. Right, so system equation of matrix. So how do we write in vector form? In vector form, we're going to use the columns in the matrix as a vector, and the variables will be the coefficient. So we have x times, try to write small because we might not have enough space, the columns. Y and z. Equal to the last column. Yeah. So that is the equivalent form for it. Right. Now in the matrix form will be very similar to the romantic matrix, in that we have the matrix of coefficient and then we times the vector variable, then equal to the last column. Yeah, so that is different forms of the same thing. Right. Now, what if we have the romantic matrix? Can we write that in different forms. This is semantic matrix. So draw about it, right? So this one doesn't have the variables. So let's say x1, x2, and x3 are the variables. If that's the case, then we use that as the linear combination. So x1 first column, x2 second column, just the linear combination of the columns, x3 third column, equal to the last column. Right, so linear combination of those columns equal to the last column is the linear combination of the columns in the matrix. Of course, we can write in the matrix form as well. The purpose of this exercise is to get comfortable switching between different forms of the same thing. And of course, from that to write the geometric matrix should be the system equation should be actually from any of them should be easy. 1x1 plus 4x2 plus 5x3 equal to -7. No x1 4x2 plus 12x3 equal to 4. 4x1 6x2 minus 2x3 equal to 3. Right. So when we have one of them, we can write the rest of the form. Right. Let's say this one. How do we write that as the geometric matrix or system equation or that? Of course, if we multiply this out, that would be easy. And combined, we have this. But let's say if we write this as the geometric matrix or the matrix form, it doesn't matter. So this, since the last column is the linear combination of those columns, so we're going to put those columns into a vector, into a matrix, I mean. And UVW as the matrix of variables, right? Of course, the matrix form and the geometric matrix will be very similar. Yeah, just the left hand side will be the same thing as the matrix. You see 1 -3 4 1 2 0 0 3 4 and 2 7 0. Yeah, so system equation, of course we can prevent by any of this. Right, so right, 1u 1v, it's easier to write, just write a variable on the top of it. So 1u 1v no w equal to 2, negative 3u, 2v, 3w equal to 7, 4u, no v, 4w equal to 0. Yeah. Finally, if we have the system equation, we can write as any of the forms. So I will write the system equation first. So for x1, 5x2, no x3 equal to 1. The next one, 1x1, 4x2, 9x3 equal to negative 3. And then 2x1 minus x2, 0x3 equal to 4. Right? Now, I want to write this one first, so we just want to show you real quick another way to write from system of equations into different forms. So a way we do this is I look at all of this, factor out the x1 pretty much. The vector will become, just factor on the x1 out. For the first one, we have 4, 1, and 2. Now factor x2 out from this column. What vector do we have? 5, 4, and negative 1. Which of course we can also use the matrix equation here. And then from this we factor out x3. There's no x3 on the first one. There's 9, and there's none. There's 0 here. And equal to 1, negative 3, and 4. Yeah. Like I said, you should be comfortable with interchange between these different forms here. Of course, the augmented matrix and the matrix equation are almost the same. The numbers 4, 5, 0, 1, 4, 9, 2, negative 1, and 0. Augmented matrix 1, negative 3, and 4. Right. So you see, after this section, you should be able to write one form into different things. Again, the vector form will be, the vectors will compose of the columns of the vectors, and the last column is after the equal sign. In that case, we say this column is the linear combination of the other column vectors if the system has the solution. And the solution will be the weight of that linear combination. Right, so now we can write the same thing in different forms. What do we say if that system has a unique solution? Right, so here we have the second exercise here is that given this system has a unique solution, what conclusion can we make? It is easy to solve for it. We're not going to solve for it. We just say, what can we get from here? Right. So if this has a solution, let's say, can we write this as our augmented matrix? If this is a unique solution, we will write as the augmented matrix, right? if this has a unique solution, section 1.2, what condition for unique solution? So if it is unique solution, when we do the reduced row echelon form, we cannot have free variable, because if we have free variable, one of the variable can be freely chosen. So that gives us infinitely many solutions. So if we cannot have, if this system cannot have free variable, that means all of the variables must be basic, right? All the variable must be basic. That means when we do reduced row echelon form, we might have something here, or there. It doesn't matter. I mean, this can be anything. Usually, for if it can be anything, I just use a star. Don't write a square there. So this could be any number here, any number here, any number there. But we have to have the pivot here, so unique solution implies that no free variable. Meaning that all variables must be basic. That means the pivot in every column corresponding to each variable. So that means x1, x2, and x3 are basic variable, and those are basic because they have the pivot, meaning they have to have pivot on that column. Right. So in terms of augmented matrix, that's what we can conclude. Of course, those can be any numbers, but these have to be in this form on the left hand side. Right. That's first. The second conclusion we can make is that since this has a solution, this vector is the linear combination of the columns here. And so that is the first conclusion we can make. The second one, we say the vectors 5, 2, 5 is the linear combination of the columns. Is a linear combination of the columns of A. I'm just going to list that. I should do that correctly. Right. So the vector is a linear combination. Of course, we can write as a linear combination. But if it is a linear combination, then we say the vector 5, 2, 5 belong to the span of the three vectors. Those are equivalent. If it is a linear combination of the vectors, that means it will belong to the span of the vectors, which is the columns from the matrix. Right. So those are equivalent conclusion we can make given that this has a solution. It has a solution, then it is a linear combination. And if it is a linear combination, it will belong to the span of those vectors. And especially on this one, it is the unique solution, so we know that all the variables will be basic, so there will be the pivot on each one of them, so there's no free variable. With that, we complete section 1.4. See you in another video in linear algebra. As always, thank you for watching.